after discussing the normal random variable, we will today talk about the exponential random variable, a continuous random variable x whose PDF for some lambda greater than 0. Please note that the parameter has to be positive. Then f x equal to lambda e raised to minus lambda x for x non-negative and 0 otherwise is said to be exponentially distributed or has an exponential distribution, whichever way you want to say it. Okay. So, again we validate that this is a PDF, indeed a PDF. So, it is non-negative, right, since lambda is non-negative. So, therefore, by definition this is non-negative, and the integral from 0 to infinity lambda e raised to minus lambda x dx would be minus lambda upon lambda e raised to minus lambda x 0 to infinity. So, at infinity it is 0, at 0 it is 1. So, and with the minus sign, so minus minus plus. So, this is equal to 1. So, this is indeed a PDF. Then you want to compute its distribution function, and here this would be 0 to a, right. So, this is probability x less than or equal to a, therefore, this is integral 0 to a, and this again comes out to 1 minus e raised to minus lambda a greater than or equal to 0, right, because our variable itself is non-negative. Now, we verify the conditions that CDF must satisfy, and so limit f a as a goes to plus infinity is 1. From here you see, as a goes to infinity, this will go to 0. So, this reduces to 1, and I should have also written down the limit f a as a goes to minus infinity. As a goes to minus infinity, see, we have anyway said that x is less than, I mean for x less than 0, there is no mass, and then can I say it from here, if a is less than 0, then of course, this integral is not defined. I mean if a is less than 0, then this integral is 0, or you can argue that this is there is no mass for x less than 0. So, limit f a goes to this is 0. Okay. Yeah, fine. Then f x is monotonically increasing. So, therefore, you take the derivative of f prime of f x, which is f prime x, that will come out to be lambda. Okay, you are differentiating. Yeah. So, your f x would be, well, you treat a as x, does not matter. So, if you are differentiating this, yeah. So, the lambda would come here minus lambda. So, minus lambda and minus plus e raised to minus lambda x, and since lambda is non-negative, right, because lambda is greater than 0. So, therefore, this is again non-negative, and so the function is monotonically increasing. So, all the properties of a cumulative density function have been are satisfied. Okay. Then we find out the expectation of the random variable, and that will be integral lambda 0 to infinity, integral 0 to infinity x e raised to minus lambda x dx, and by integration by parts I treat this as a first function. So, this will be this, and now you see that at 0 this is 0. So, therefore, and this is 1. So, the product is 0. At infinity e raised to minus lambda x goes to, or if you can write it as x upon e raised to lambda x, then e raised to lambda x goes to infinity much faster than x does. So, the ratio tends to 0. So, therefore, no contribution from this term, and you are left with just this. So, therefore, again when you integrate minus 1 upon lambda e raised to minus lambda x 0 to infinity, that gives you 1 by lambda. So, the way to remember is that if lambda is the parameter for the exponential distribution and it is defined in this way, then the inverse of the parameter is your mean or the expectation. Okay. Some places people define it as 1 by lambda minus 1 by lambda x. So, in that case your expectation will become lambda. So, it is the inverse of the parameter. So, whatever you use for defining this, the inverse of that will come out to be the your. Okay. So, then to find out the variance, you find out expectation x square, and I have not done the calculations here, but again in the same way you will have to do 2 iterations of the integration by parts. Here x square is the second function, this is the first function, and you continue doing it. So, then that comes out to be 2 by lambda square, and therefore, variance is 2 by lambda square minus 1 by lambda square, which is equal to 1 by lambda square. Okay. Yes. So, a quick example, normally this would be associated, this distribution would, because when you go to any public place where there is a service counter, for example, post office or railway booking and so on. Now, of course, it is mostly online, but still people have to go to counters for all these services. Then the time that the clerk will take to service the customer is most of the time a random variable, and so exponential variables do model that situation in quite a few this thing. So, suppose the length of service at a post office counter in minutes is an exponential random variable with parameter lambda equal to 1 by 15. So, immediately you can say that the expected number of time that the expected duration of a service to a customer would be 15 minutes, right, because the expected mean the expected value of this random variable would be 1 by lambda, which is 15 minutes. Okay. If someone arrives immediately ahead of you at the counter, find the probability that you will have to wait 15 minutes between 15 and 30 minutes. To find the probability that you have to wait for 15 minutes, that means at least 15 minutes, right. So, therefore, the event would be x greater than or equal to 15, where x is your time for having to wait. So, probability x greater than or equal to 15, which will be equal to 1 minus probability x less than 15, right. Okay. And therefore, as we have computed this already while computing this for the for x less than x exponential distribution. So, this will be 1 minus of 1 minus e raised to minus 15 by 15, right, because your lambda is 15. So, therefore, this probability comes out to be e raised to minus 1, which is 0.368, right. Since, as I have said, that because we have already made this computation, that this will be equal to 1 minus e raised to minus 15 by lambda, and your lambda is 15. So, therefore, this will be equal to e raised to minus 1, and so this is 0.368. So, similarly, for the second one, probability 15 less than or equal to x less than or equal to 30. That means, your waiting time is now between 15 and 30 minutes, 15 minutes and 30 minutes. So, that will be again by the same computations will be f 30 minus f 15. And which again would be 1 minus e raised to minus 2, because it will be 30 by 15, which is minus 2, and then this is 1 minus of 1 minus of e minus 1. And so, because this is less than or equal to 15, and so less than or equal to 15, less than 15 for a continuous distribution. So, it will be this will be the probability, and so it is e raised to minus 1 minus e raised to minus 2, which is 0.233. Now, I want to show you another important property of the exponential distribution. So, first of all, we will talk about the memoryless property, and we say that a random variable x is said to have the memoryless property if probability x greater than s plus t, given that x is already greater than t, is equal to probability x greater than s for all s and t non-negative, which means that it does not matter how long you have already waited. If you are asking for this probability x greater than s plus t, then it is the same as probability x greater than s. So, therefore, the system does not have the system we are modeling does not have a memoryless property, and so we are talking of a random variable whose distribution satisfies this condition. So, now I will show you that the exponential distribution among all continuously distributed random variables or among all continuous PDFs, exponential distribution has the property of being memoryless. distributions which are discrete and which also have the memoryless property, but among continuously distributed random variables, a random variable which is exponentially distributed has the memoryless property. So, in case this random variable is exponentially distributed with parameter lambda, then you see if you write down this expression probability x greater than s plus t, given that it is x is greater than t, then this will be this, because when the product of these two would be intersection of these two events would be x greater than s plus t, right, you would, because it is t smaller than s plus t. So, this reduces to this expression, okay, x greater than s plus t divided by x greater than t. Now, by our definition this is because f a is 1 minus e minus lambda a. So, 1 minus f a would be simply e raised to minus lambda a. So, here it is e raised to minus lambda s plus t divided by e raised to minus lambda t, and which is this, which is equal to probability x greater than or equal to s. So, exponential random variables are memoryless, and in fact, a little more arithmetic would be required or calculus to show that if you impose this property, then you can actually show that only exponential random variables have the memoryless property. So, since this being a first course, I am omitting the mathematics here, but those interested can sit down and work it out and see that when you start with this condition for a continuous random variable, then you will see that only exponential random variables, the PDF which will satisfy this condition will actually be the exponential PDF. Okay. So, let us again look at an example. Suppose that the number of hours before a transistor fails is exponentially distributed with mean 500 hours. Okay. So, here the lambda is 500. If a person desires to go on a long trekking trip of 300 hours and uses the transistor in his radio, then we want to find out what is the probability that the transistor will not fail. So, what is the probability that the person will be able to complete his trip without having to replace the transistor? So, he wants that the probability that the transistor will not fail for the 300 hour long trekking trip that he is undertaking. So, let us find out the so the solution is that f x is 1 upon 500 e raised to minus 1 upon 500 x, because in the problem it says that the hours, the lifetime of the transistor is exponentially distributed with mean 500. So, as I was telling you, if the mean is 500, then the parameter will be 1 upon 500. So, therefore, the PDF of the random variable representing the lifetime of the transistor would be given by this, fine, x non-negative. So, therefore, probability x greater than 300 is simply e raised to minus 3 by 5, because it is e raised to minus 300 upon 500, which is e raised to minus 3 by 5, and you can compute this value from the tables or. Okay. So, what can be said when the random variable is not exponentially distributed? In that case, the memoryless property is not there, and so this will be simply a conditional probability in terms of capital F, and so that is it, right. So, you see the advantage of having a random variable which is memoryless. Okay. Now, another thing that is useful and can be again for exponential random variable, it gets quite simplified, and that is the hazard rate function, or sometimes you also call it the failure rate function. Okay. So, if x is the random variable which is representing lifetime of some item, and of course, it is a non-negative variable, and the PDF and the CDF, the PDF is given by small f and CDF by capital F. Then hazard rate function called the failure rate function is denoted by lambda t and is defined as follows. So, lambda t is small f t, that means the PDF divided by 1 minus CDF, right. So, and a simple explanation is possible. So, here again what we are saying is that x belongs to, this is a bracket here, t plus delta t is very small, and then given that x has already worked for t, now what we are saying is that it will fail just after t, because t plus delta t. So, x lies in the interval t comma t plus delta t, given that it has been functional till time t. Okay. And so, this is a probability x belongs to t comma t plus delta t. Delta t is a positive quantity, very small. So, therefore, when you take the intersection of these two, you get this event divided by probability x greater than t, and so this will be, by our definition, f t plus delta t minus f t divided by 1 minus f t. Okay. So, now you see the limit of this as delta t becomes smaller, then you divide by delta t and multiply by delta t. So, this divided by delta t, remember limiting value of this is the derivative of f at t. So, which becomes f prime t into dt upon 1 minus f t, and f prime t is your PDF f small f t divided by 1 minus f t dt. So, therefore, the definition of the failure rate, because as you see that it should fail just at t time t. So, it has been functional up to time t and then it fails. So, now if f t is exponential, you see when you write out this will be f t small f t. So, the PDF is mu e raised to minus mu t. I have used symbol mu because lambda is already being used here, fine, and this is 1 minus f t will be e raised to minus mu t. So, you see this is mu a constant. So, for an exponential random variable, the hazard rate is a constant, it is not a function of t. Otherwise, as you see that this will be a function of t. So, the hazard rate function is dynamically changing depending on the time, that means if you are talking of lifetime. So, as it should be, but for exponential distribution, the explanation is simple, since it is memoryless, therefore, the hazard rate function does not change, it is a constant. So, this is the rate of change of this is the rate of failure, and so because it is memoryless, it does not matter how old the instrument is, the probability of its failing any time is same, and so here the rate is also constant. Mu is therefore also referred to as the rate of the exponential distribution. So, now mu is the parameter, this is also the rate of failure for an exponential distribution, and we saw that 1 upon mu will be the mean of the exponential distribution. So, given hazard rate of function lambda t for a continuous random variable, it is possible to determine its PDF. Okay. So, we will just show, because you see lambda t I can write as d dt of f t 1 upon 1 minus f t, right, and then if I take the integral of both the sides and attach a minus sign. So, there is a minus sign here, this is 0 to x lambda t dt, and this is integral 0 to x minus f prime t. I have written this as f prime t dt upon 1 minus f t. Okay. Now, by formula for integration, because derivative of this is this, therefore, this will be ln of 1 minus f t, right. So, therefore, ln of 1 minus f x, because you are computing from 0 to x. So, it will be 1 minus f x will be, and this is integral minus 0 to x lambda t dt. I hope this is clear, because see this will come out to be ln of 1 minus f t, and this is from 0 to x. So, 0 to x, when you put x here, this will be ln of 1 minus f x, and at 0 f 0 is what? F 0 is 0, right. So, ln of 1 is 0. So, therefore, the contribution from here you get is ln of 1 minus f x. Yes, remember limit f x as x goes to minus infinity is 0. Okay. So, therefore, I am just using that. So, that reduces to ln of 1 minus f x, and this on the right hand side, this is minus 0 to x lambda t dt. So, therefore, you can say 1 minus f x is equal to e raised to minus 0 to x lambda t dt, right. Okay. And so, f x you can write down from here as 1 minus of e raised to minus integral 0 to x of lambda t dt. So, if I know lambda t, then I can integrate here, and then my f x will be of this form. Okay. So, that means it is enough if you know the hazard rate function of a random variable, you can determine its distribution. So, once you know the cumulative density function, you can determine the PDF also, right. Now, I will just illustrate the concept some more through an example, and this says that see, it is said that the death rate of a smoker is at each stage twice that of a non-smoker. That means, they say that your age gets reduced by half if you are a smoker compared to what a non-smoker. So, what is the ratio of the probability of a non-smoker to that of a smoker to that of a smoker of surviving up to the age of. So, suppose I am just saying that both of them surviving up to the age of 60, given that both have survived up to 50 years, we want to find out the probabilities. So, maybe the ratio part is not important, all I am saying is let us find out the probabilities that a non-smoker will survive up to the age of 60, given that he or she has survived up to 50 years. Similarly, a smoker, the probability, what is the probability of a smoker surviving up to 60 years, given that he has survived up to 50 years. So, I will define lambda s t as the hazard rate of the smoker and lambda n t as the hazard rate of non-smoker. So, now let me just right now take, instead of 50, just let me take some years age a. So, what we are saying is that the probability that a non-smoker's lifetime is more than 60 years, given that the lifetime of the non-smoker has been more than a, is the conditional probability, right. Because again the intersection of these two, because 60 is more than a. So, this is a probability that the non-smoker has been the lifetime would be more than 60. So, that becomes 1 minus f n 60 divided by 1 minus f n a, right. And from here you see this is 1 minus f x is e raised to minus integral 0 to x lambda t dt. So, that will be 0 to 60 lambda n t dt, right, and 1 minus f n a will be 0 to a lambda n t dt e raised to, right. So, this is what we just computed here, and therefore, if you take this upstairs, then you see the integral, this will become e raised to a to 60. So, this will be e raised to minus integral of a to 60 lambda n t dt, and this let me call as P n. So, the probability of smoker surviving up to the age of 60, given that he has already survived up to the age of a, right. And correspondingly, for a non-smoker, for a smoker, this probability of having survived of surviving up to 60 years, given that he has survived up to a years, is lambda s t dt, and I am calling it as P s. Okay. So, if the belief is that lambda s t is twice lambda n t, that means the rate of the death rate is twice as high for a smoker compared to a non-smoker, then I substitute lambda s t for lambda s t twice lambda n t here. So, that will be twice lambda n t, and so this will become square of, I have not written the step, I mean actually this is equal to e raised to minus a to 60 lambda n t dt square, right, which is the probability P n square. So, the effect is that the probability gets squared up for a non-smoker. So, the probability of surviving up to the age of 60 is a square of the, for a smoker is square of the probability of a non-smoker surviving up to the age of 60. So, this 50 was not really important, because a could be anything here. So, given that is why we said that at any stage, at each stage. So, therefore, it does not matter when you are making this comparison. So, however old both the people are, after that if you want to say what is their age of surviving up to 60, then the probability for the smoker is square of the probability for the. So, now here as I said that if you take lambda n t to be 1 by 30, that means remember I am taking the situation when Yeah. So, that means this is now because this is constant. So, therefore, I am taking the exponential situation, that means a random variable, the lifetime is a random variable is exponentially distributed. Then probability that a non-smoker reaches the age 60 would be, yeah, because this is lambda and t is 1 by 30. So, you want to compute, will it come out to be e raised to minus 1 by 3? Yes, e raised to minus, you are saying this is 50, 60 and 1 by 30 dt. So, what will that be? 1 by 30 into 10, right. So, this is I mean e raised to minus. So, this is e raised to minus 1 by 3. Okay. So, if it is a constant, that means it corresponds to exponential random variable, and so this is e raised to minus 1 by 3, which turns out to be 0.7165. So, for a non-smoker, and for a smoker it will be the square of this, which will be 0.5134. So, see how fast the probability has reduced because the person is smoking. Okay. So, the probability of a smoker surviving up to the age of 60 is 0.5134, and for a non-smoker it is 0.7165. So, that way one can have many more applications, and as we go along, maybe I have put some problem related to hazard rate function in your exercise 4 also. Okay. Now, we continue with some more special continuous random variables, and the next one is the gamma distribution, and X is said to have gamma distribution with parameters alpha and lambda. Both the parameters have to be positive. PDF is given by this equation. So, f x is lambda e raised to minus lambda x in raised to alpha minus 1 upon gamma alpha, and that is why the name. So, this is let me show you the calculation for gamma alpha. So, let us compute the value of gamma alpha for alpha greater than 1. So, therefore, the definition is this is equal to 0 to infinity e raised to minus y raised to alpha minus 1 dy, right. So, integration by parts, and therefore, this will be the derivative here is e raised to minus y should be minus, yes. So, here this is minus e raised to minus y raised to alpha minus 1, 0 to infinity, and then this becomes plus because minus minus is plus. So, therefore, this will be plus 0 to infinity, then derivative of this is alpha minus 1 y raised to alpha minus 2 e raised to minus y dy. Now, let us compute the values at the two limit points at the end points. So, for y equal to 0, see this will be 0 because alpha is greater than 1, and that is why it is important. So, alpha is greater than 1, therefore, this is a positive power. So, therefore, this is 0, and of course, at 0 e raised to minus e raised to 0 is 1. So, this is equal to 0, right. And again when y goes to infinity, then this goes to infinity faster than this here again, because alpha is greater than 1. So, this exponent is positive, and therefore, this will go to 0. So, therefore, no contribution by this term, and so your integral. So, gamma alpha reduces to just this, which by our notation will be gamma alpha minus 1. Should have written, yeah. So, therefore, I did not write, yeah. So, here iteratively that means this integral will be now alpha minus 1. Okay. And so, for positive integer values of alpha, if I go on doing it iteratively. So, for integer values of alpha, positive integer values of alpha, this we can see is gamma alpha would reduce to alpha factorial alpha minus 1. You can see that because as go on. So, the finally what you have will be this will be then I should have yes, this is alpha minus 1. So, this should be equal to alpha minus 1 gamma alpha minus 1, right, from here alpha minus 1. Okay, fine. So, therefore, as you go on the next iteration, it will be gamma alpha minus 2, and so as you go on, alpha is a positive integer. Therefore, you will end up finally with just integral 0 to infinity e raised to minus y dy, and so this will reduce to this will reduce to alpha factorial of alpha minus 1 for alpha being positive integer, right. Now, it can also be shown that the gamma function is defined for alpha between 0 and 1. This is also possible. We can also show that the integral is defined, that is it will be a finite value. So, for all values of alpha between 0 and 1, the integral is also defined. That means, gamma alpha is defined for alpha between 0 and 1. And one important value is gamma 1 by 2, which is root pi. And this integral we will obtain these values later on in the forthcoming chapters. So, I will talk about fractional values of gamma alpha, alpha between 0 and 1. And there are tables available for values of fractional values of alpha. There are tables available, non-negative fractional values of alpha, tables are available, right. And for alpha equal to 1, the gamma distribution reduces to the exponential distribution. I will have to check the, see our gamma PDF is given by this. So, when you put alpha equal to 1, this term is gone, and so your PDF reduces to lambda e raised to minus lambda x, and gamma alpha is also 0, I mean sorry 1. So, therefore, you will be the gamma PDF reduces to lambda e raised to minus lambda x for x non-negative. So, therefore, for alpha equal to 1, the gamma distribution reduces to the exponential distribution. So, this is one relationship, and then I will show you some other relationships between many other this thing. Now, you want to again check that this PDF is a valid PDF, and therefore, I have to show that this integral will be evaluated to 1. So, here of course, you put lambda x equal to y, then lambda dx is equal to dy, and immediately this integrand reduces to e raised to minus y, lambda dx gets replaced by dy, and this is y raised to alpha minus 1 upon gamma alpha. And so, from here you see that divide by gamma alpha here, then this is equal to 1. So, the validation is complete. Okay. So, therefore, this is a valid PDF, and now you want to compute the expectation of this gamma random variable, then you have to multiply this by x and integrate, but then it is easy to manipulate, because I will add x to this and lambda also. So, I divide by lambda, then I multiply by alpha and multiply here by alpha. So, this becomes gamma alpha 1 by our definition, right. So, this will be gamma alpha 1, and this will be lambda x raised to alpha. So, then this will be that means the PDF of gamma, here now your parameters are alpha plus 1 and lambda, right. So, therefore, since the this is again a PDF for gamma alpha 1 comma lambda. So, again it will integrate to 1, and so you will be left with alpha by lambda. So, the expected value of alpha lambda gamma variable is alpha upon lambda. Okay. So, that means, if the convention is to write this first and then this. So, then this divided by this, that is, if you are taking the gamma distribution alpha comma lambda. Okay. Then similarly, expectation x square can also be just by a simple manipulation computed immediately. What I will do is, I need lambda square here to bring this together with this. So, then I divide by lambda square and I multiply by alpha alpha 1 to make it gamma alpha plus 2, and this will be lambda x raised to alpha plus 1. So, again this is a PDF of gamma alpha plus 2 lambda. So, this will integrate to 1, and I will be left with alpha into alpha plus 1 upon lambda square. And so, variance will be this quantity minus alpha lambda whole square, and that gives me alpha upon lambda square. So, simple calculations to tell you the required quantities. Okay. Now, let me just show you an application, and this application may be I will be using a concept which we have yet to do, but does not matter. I still thought that this will be a good time to mention this application. So, here see the case, this is we are considering the case when alpha is a positive integer, when alpha is equal to n is a positive integer. Okay. Now, gamma distributions arise as the distribution of the time one has to wait until a total of n events have occurred. So, it is like you go to a railway booking counter and railway ticket booking counter, then you have people ahead of you in the queue, and each person, as I told you that we will treat the service time as a random variable. So, and remember that I had shown you that the service time being a random variable can be an exponential random variable. So, for each person the service time is a random variable, and then since they are different people, independent people. So, each one gets serviced. So, then the total time would be sum of that many independent random variables and exponentially distributed random variables. This is the idea. So, now what I am trying to show you is that the gamma variable is actually the time one has to wait till all people ahead of you have been serviced and you have also been serviced. So, the way we will measure it is that, so when I am saying alpha equal to n, so here I will be counting that you also have been serviced. So, then until a total of n events have occurred. Okay. And of course, later on when we do the Poisson process and so on, then the whole thing will become much more clear, but you can just get a feeling for the application that I am trying to discuss here. So, now let T n be the time at which the nth event has occurred. Okay. So, time at which nth event occurred. So, then T n less than or equal to t, this event would that mean if and only if all the n events have occurred by time t. Right. T n is the time at which the nth event occurred. So, now T n less than or equal to t will mean that by time t all the n events should have occurred, which means in our particular case all n people have been serviced by the railway ticket booking counter. Now, let capital N t be the number of events in 0 t. So, see in this particular case, if there are people ahead of you, let us say n minus 1 people ahead of you, you are the nth person, then that means and the time span that you are taking is 0 to t, then that many people should have arrived in the time 0 to t. When there are n people in the system, then only they get serviced. This is how we. So, in this case there are n arrivals in this time, right. Okay. And so, when we look at probability T n less than or equal to t, if you want to compute this probability, then this is the same as probability n t greater than or equal to n, because at least n events in 0 t, that means at least n arrivals must be there. There can be more, but when you are talking of n people to be serviced in this particular time span of time, then that at least that many people should have arrived, or that many events must be there in the system. So, this is what it is, right. And this we will therefore, because this is a discrete thing, people arriving is a discrete are discrete events. So, j this will be j from n to infinity, probability n t equal to j, right. Probability that there are j people in the system at time 0 t, and then you sum it up from j equal to n to infinity. Now, this is the part. See, very often when you talk of events, discrete events occurring in a span of time, under certain conditions, it can be shown that these will be Poisson arrivals. That means, the number of arrivals in a span of time would follow a Poisson distribution, and therefore, probability n t equal, and this I will prove hopefully when we are talking about stochastic processes and so on. So, then in detail I will discuss how you arrive at this probability, right. When you are under certain assumptions, you can show that the probability n arrivals in the time 0 t would be given by this. So, you sum it up j to n. So, it means for n t equal to j, essentially n t is a Poisson random variable, and so the mean value becomes lambda t, because you are taking the span 0 t. So, this will later on be explained. So, therefore, this is your Poisson probability, you sum it up from n to infinity, right. Now, this is your cumulative distribution function for T n. To find out the PDF, I will take the derivative, which is f T n of t, and so we differentiate this expression with respect to t and you see if you first differentiate this, then lambda comes out and j. So, j lambda e raised to minus lambda t raised to j minus 1 divided by j factorial minus derivative of this, which will be lambda minus lambda e raised to minus lambda t raised to j divided by j factorial. And here j varies from n to infinity. Okay. And so, just rearrange the things a little bit, j when cancels out here. So, it will be j minus 1 factorial lambda t raised to j minus 1. So, what you see is that here the terms are from starting from j minus 1 and here it is j. So, you see things will cancel out in pairs and except the first term here will be left out, which will be lambda e raised to minus lambda t raised to n minus 1 divided by n minus 1 factorial. That is the only one, because when you put j equal to n plus 1 here, that will be lambda t raised to n upon n factorial, and here also j equal to n, it will be n factorial and lambda t raised to why is it j minus 1 here? I was subtracting, so this will be j, sorry, because when I am differentiating with respect to this one here, then lambda t raised to j remains intact. So, this is it. So, when j, so therefore, this term will cancel out with the second term here, and then the third term here will cancel out with the second one here, and so this will process will go on. Only the first term will be left out here, which is lambda e raised to minus lambda t raised to n minus 1 upon n minus 1 factorial. So, this is now a gamma distribution with parameters n comma lambda. So, therefore, the amount of time a person has to wait till he is serviced, and if there are n minus 1 people ahead of him in the queue, and so that is a random variable, and we have just now shown that when the arrivals are Poisson, then this will be a gamma distribution with parameters n comma lambda. So, in this case, this is also referred to as an N-Erlang distribution. That is another name in literature. You might some books may refer to this distribution as N-Erlang. Okay. So, we have got some feeling about the gamma distribution, and as we go on, I will give you some more insight into the thing. Now, the other continuous variable distribution which is of importance is the beta distribution. So, a random variable x with PDF given by the equation f x x is 1 upon this is a beta function a comma b x raised to a minus 1, 1 minus x raised to b minus 1, x between 0 and 1 and 0 otherwise. The integral we denote by b a comma b. So, this is 0 to 1 x raised to a minus 1, 1 minus x raised to b minus 1 dx, where a and b both are positive. Now, again just as for the gamma distribution, we can show that for a greater than or equal to 1 and b greater than or equal to 1, the integral will converge, and in fact, for integer values, just like we did for the computation for gamma distribution, it can be shown that this integral will be equal to gamma a gamma b by gamma a plus b. So, therefore, I should again correct my statement here, and that is that the beta PDF is this function divided by this. So, it becomes gamma a plus b divided by gamma a gamma b, and therefore, the integral will turn out to be 1. So, the the beta PDF is actually this divided by this number, and so we denote this integral by b a comma b, which is, so therefore, it is since it is defined for all a b positive. Now, for a greater than or equal to 1 and b greater than or equal to 1, you can show by integration by parts that the integral will converge, and for and will be equal to this. Okay. And for fractional values of a and b, also it can be shown that this is defined, the integral is defined, and it is equal to gamma a gamma b upon gamma a plus b. Right. Now, many useful applications of the beta distribution, and in one case is that it models random phenomena whose set of possible values is some finite interval c comma d. So, that means all possible values of this random phenomena occur between within a certain interval c comma d. And but then since we have here defined the variable to be from 0 to 1, so then by scaling and shifting, we can transform this interval to 0 1, and of course, one obvious transformation is that y is equal to x minus c upon d minus c. So, then all possible values of x which are within C d will now be. So, the corresponding y variable will have all values between 0 and 1. So, and then we will see further applications of the beta distributions, and will compute the other quantities related with the beta distribution. Now, I am just trying to give you pictures of or graphs of this beta distribution for different. So, now when a is equal to b, this graph is symmetric. The graph of the beta function is PDF is symmetric, and for example, a equal to 3, it will be something like this, and as a becomes bigger, the mass gets concentrated, this the graph becomes narrower, and this is symmetric, right. So, if you draw for a equal to 10, probably it will be something like this, the peak will be higher and so on. Now, for a not equal to b, the graph is asymmetric and skewed towards the left. So, for example, a equal to half, it is almost skewed towards the y axis, and as a increases, again the skewness shifts to the center, and these of course, they are not the graphs are not drawn to scale, but in any case a upon a plus b is equal to 1 by 20. So, in this situation, when suppose a is 6, you can find out what the value of b is, and so on. Now, there are situations, see for example, if you have a big project in which you have lot of jobs, and so of course, a big project will be made up of a number of jobs, and this project may not have been handled completely before. So, there is lot of uncertainty about the job completion times, and as a project manager, he or she has to sometimes have some estimate as to how long it will take for the whole project to be completed, which means that must have a good idea as to how long it will take for each job to be completed. Now, in the absence of any previous experience, because the jobs have not been performed, for example, of course, this is now a very old example, that when they were trying to put a man on the moon, then it was a completely new project, all the jobs that made up the project were all new. So, people had no idea about the how long it will take for the jobs to be completed, but certainly there is a certain finite span. And then of course, you do not expect, just like as for the normal distribution, for example, it is a symmetric distribution, but then here there was no reason to believe that the completion time distributions will be symmetric. So, therefore, beta distributions fitted the bill very well, because here was a distribution which has a finite span, and even though it is a continuous distribution, and then it was not symmetric, so and so on. So, then huge projects were then the time estimations were made using beta distributions. So, interesting applications, right. So, where job completion times are not predictable, you have no idea. Then again, by integration by parts, you can show that expected value of x is a upon a plus b, and variance x will be a b upon a plus b into a plus b plus 1. Okay, so, beta distributions again, if one gets time, one can talk about, I can give you an idea how the time estimates are done using beta distributions. Okay. Now, as we go along, we also need to keep coming back to distributions of function of a random variable, and I will just do some sample functions here, and then try to give you a general result. So, let us say suppose x is uniform 0 1, then that means x is taking non-negative values. Then if you define the function y equal to x raised to n, then obviously x raised to n will also remain in the interval 0 to 1. That means, the range for y is between 0 and 1. And so, if I want to find the PDF of y, then probability y less than or equal to small y is the same event as probability x n less than or equal to y, and this will be probability x less than or equal to y 1 by n. So, remember this is okay, because the values here are non-negative. So, this is the same as this inequality. the nth root, right. And now, if you differentiate both sides, this will give you the PDF of y, and here when you differentiate this will give you the PDF, because this is now f x, right. This side is f x y 1 by n. So, you are differentiating with respect to y, and so this is f x y raised to 1 by n into the derivative of y 1 by n, which is 1 by n, y raised to 1 by n minus 1, and y between 0 and 1. So, but for a uniform random variable, this is equal to 1, right, and therefore, the PDF of y reduces to 1 by n, y raised to 1 by n minus 1, when y is between 0 and 1 and 0 otherwise. Okay. Take another function. So, now when you take the function y equal to x square, in this case you are not saying that x can only take non-negative values, x can take negative values also. Then you see, when you write down this event probability y less than or equal to small y, which is probability x square less than or equal to y, then this will be then equal to this event, that capital X is between minus root y and plus root y. Because I did not, if I had sort of put the restriction that x has to be non-negative, then obviously it would have been just this part would not have been there. But since I am allowing x to take all positive negative values, therefore, this will be equal to this event, right. And so, by again our this thing writing down in terms of the cumulative density function, this will be f x root y minus f x of minus root y. Okay. And then, so we differentiate again with respect to y, and d d y f y y is so here this will be f x root y, and then the derivative of root y, which will be 1 upon 2 under root y. Okay. This is x, and plus f x minus root y. So, the minus will become plus, because there is a minus coming from here, there is a minus here already. So, plus f x of minus root y into 1 upon 2 root y. Okay. So, this will be your PDF for y equal to x square. Now, the third kind of function that I am looking at here is y equal to mod x. So, x has a PDF f x, then here, and so in this case y will have non-negative values, even though x has negative values, right. So, we write down the event probability y less than or equal to small y. This is probability mod x less than or equal to y, which again can be written as x between minus y and y, right. Because the absolute value has to be less than y is a positive number. So, therefore, in magnitude the value x, even if it is negative, it has to be higher than minus y, right. Because if you are saying that mod x should be less than or equal to 3, then your x cannot be minus 4, because the absolute value of x would be 4, which is not less than 3. So, therefore, the values of x have to be between minus y and y, right. And therefore, this is f y minus f of minus y, and when you differentiate with respect to y, you get PDF of capital Y, which is f x y. Again, minus sign gets converted to plus, because there is a minus coming from the derivative of minus y. So, this y greater than or equal to 0. So, one can go on, but then I will just summarize all this in this theorem, yes. So, this is x is a continuous random variable and f x its PDF. Suppose g x is a strictly monotone increasing or decreasing function. So, this is now very clear and it is differentiable. So, strictly monotone means that it is either going like this, a function like this, or it is coming like this. So, monotonically decreasing or monotonically increasing. Then the random variable y equal to g x has a PDF given by this, and it will take a few minutes to just prove this result. So, in this I just realized that in the statement of the theorem this absolute value sign is missing, but that is important and I will show you why. So, that means when y equal to, when you are looking at the function g x of the random variable x, and we are finding the PDF of y, then f y of small y is f x the PDF of x into of at g inverse y, an absolute value of d dy of g inverse y when y is equal to g x, and 0 if y is not equal to g x. And of course, here what we are saying is that the spurious values are not being considered, because when you take the inverse function here, see it is a monotone function. So, the relationship between, that means this would be I do not have to worry about extra values here. So, this will be fine. Okay. So, now let us look at the proof of the theorem. So, we start with the event. We start with the event that y is less than or equal to small y, which is equal to this, and this I can write x less than or equal to g inverse y. Now, because the function is monotonically increasing, so this inequality from here, this inequality is the valid outcome, right, because it is increasing. So, the inequality will not change. The function g we have assumed is increasing function, right, and therefore, this is equal to f x of g inverse y. Is it okay? So, differentiate both sides with respect to small y, then this is f y y, which is d dy of this thing, and in the next step you get this is the PDF of capital Y, which is here when you differentiate capital F x, you get small f x. So, that is g inverse of y into the derivative of this, which inverse y. And now, here because the function g is monotone, this again a result from calculus, you can show that positive derivative and f being the PDF, f x being the PDF of x, this is non-negative. So, the product is non-negative, and therefore, this is non-negative. So, this satisfies the condition, and of course, you can verify that this is also a valid PDF. That means, the integral will be 1, and so this is it. So, when you are taking the increasing function, then because this part is non-negative, I do not have to put the bar sign here, but when g is decreasing, then you see the probability, the event g x less than or equal to y will transform to x greater than or equal to g inverse y, and that is what I am showing you, that if this is the function g x, right, then you are saying g x less than or equal to y. So, g x less than or equal to y. So, beyond g inverse y are the values for which your function is less than y, right, when the function is decreasing. And so, the inequality here will reverse, and that will be x greater than or equal to g inverse y, right. And therefore, f y is 1 minus this, you will write as 1 minus f x of g inverse y, and then again differentiation both sides will give you f y y, then minus f x g inverse y and derivative of this. Now, since g is a decreasing function, this derivative would be negative. So, minus this will make it positive, and that is why it is important that we write the absolute sign here, because your PDF cannot be negative. Okay? That is the first condition, and which turns out to be, because when the function is decreasing, this will be negative. So, minus into this would become non-negative, and so here again this would be positive. Okay. So, this is for the completion's sake that I wrote down this theorem, but normally what we do is we ab initio compute the PDF, we write down the equivalent event when you take a function of a random variable, and then of course, differentiating both the sides you try to get the PDF for the function of a random variable, but at times it also helps to be able to use the theorem. So, this is this thing. Now, let me just show you as I was saying that one can either obtain results directly or using the theorem. So, if x is an exponentially distributed random variable with mean 1 by lambda, then we will show that expectation of x raised to k is k factorial upon lambda k, k weighing from 1. So, for any finite value of k, this is what you have, right. Now, a direct solution I am giving you. So, solution 1 I should have said actually, this is solution 1, which is a direct solution. So, here because I know the PDF of x, so expectation x raised to k will be 0 to infinity x raised to k lambda e raised to minus lambda x dx. Remember, we are told that the mean is 1 by lambda. So, the parameter the distribution would be lambda e raised to minus lambda x dx, and integration by parts, treating this as the first function. So, the lambda cancels, minus e raised to minus why am I writing t here? This should be lambda x into x raised to k 0 to infinity plus the minus sign, and minus sign makes it plus 0 to infinity e raised to minus lambda x, and then x raised to k minus 1 dx into k, right. So, you see this integral will come out to be this, and then I again multiply and divide by lambda. So, then this becomes my regular gamma function. So, 1 upon lambda. So, this will be I k minus 1 into k by lambda, this integral, because when I differentiate this will, the k will come out. The k should have been there. Sorry, so you have differentiated x k, so k is already there. Okay. K is here. So, that k I am writing k by lambda, and then this integral is your I k minus 1. Right. Our I k was lambda e raised to minus lambda x, x raised to k in dx, integral from 0 to infinity. So, now this integral I denote by I k minus 1, right, and therefore, your expected value of x k as you go on doing it by iteratively, here of course, k is a positive integer. So, this is k factorial upon lambda k into I 0 final, right, if I go on doing it repeatedly. So, this becomes then for if I write down for I 0, this will be k factorial upon lambda k integral 0 to infinity lambda e raised to minus lambda x dx, which turns out with this integral is 1, because anyway you know that this is the PDF of an exponential distribution with the parameter lambda. So, therefore, this integral is 1, or you can directly show that this is 1, and therefore, this is the answer, right. Now, we want to use the theorem. So, using the theorem that is that you compute the PDF of the random variable x raised to k. That means, I compute the PDF of the function of the random variable, and then through that route I try to compute the expected value. So, if I define my y as x raised to k, then I am trying to compute y less than or equal to small y, which is probability x raised to k less than or equal to y, which is then x, because everything is non-negative. So, therefore, the inequality will be converted to this, that is x less than or equal to y raised to 1 by k, and then f y y, that is the PDF of y now will be f x of y raised to 1 by k into 1 by k y raised to 1 by k minus 1, right, because this I will be writing this as f x of y 1 by k, right. And so, E y will therefore be 0 to infinity y into f y y, which is f y y dy, which I substitute for f y y in terms of f x. So, this will be 0 to infinity y lambda e raised to minus lambda y raised to 1 by k y raised to 1 by k minus 1 dy. Okay. And so, E y. So, now here I can put y raised to 1 by k as s. So, then 1 by k y raised to 1 by k minus 1 dy is ds. So, this whole thing goes to ds, and so I have now here s raised to k, right, because y will be s raised to k and lambda e raised to minus lambda s ds. And this is now we recognize that if I take lambda, divide by lambda raised to k and combine lambda here. So, lambda s raised to k, and so this is your gamma PDF, and therefore, not PDF in the sense that I must have here gamma k plus 1. So, therefore, this integral will therefore be equal to, this integral will be equal to gamma of k plus 1 and then divided by lambda k. So, that is another way of, and since this is an integer, k is an integer, positive integer. So, this will be k factorial upon lambda k, which we got here also. So, you know, whichever is convenient, one can try to get the result either way.